Okay, period 8. Mr. Davis is here to help you get through the lesson today. And to make his life easier, I'm making this video. This is day 3 of Metamorphic Rocks. And today's wrap up to this unit is to discuss not just the rocks, but how those rocks got there. And the short answer to that question is every time the Virginia was hit by something like an island arc or a microcontinent or Africa, it twisted and folded the rocks. Now, our rocks don't look like this anymore, like this photo, but they did once upon a time. It's just that the East Coast mountains are so old, they're all eroded away. So, this is what happens when rocks get hit by continents and the sedimentary rocks get folded. And if they get squeezed by those in the collision to high temperatures and pressures, then they're going to get turned into metamorphic rocks. Okay? The best way to visualize this is to watch this little video here, and I'm going to turn off the sound on that and just talk over it so you guys can see what's going on here. Okay, so here you got some big fancy mountains, and they are probably the Alps. Maybe they're in Canada, but they're young mountains. We can tell because they're pretty jagged and snow-capped. Okay, so what you have here is a sand model, and I hope you'll appreciate how much work it was to make this thing. And I think you'll actually really be impressed with it because it's a physical model. It's a real thing. It's not a computer model that might be like reality. What you're going to see is reality. And in that regard, it's somewhat more convincing than a computer model to help us understand how mountains form. There's another great advantage of it, or a disadvantage of it. The disadvantage of a model like this is that it actually probably took hours, or maybe even an entire day, just to set this up and then run it. And if you wanted to try to change something a little bit and run it again to see if that variable would influence the structures or how it behaved, you'd have to do it all again. Whereas in a computer model, you could just change a few equations and parameters and variables and then run it again. And you could do it 100 times in an hour and see how that sensitivity, how sensitive the model was to those changes. But you can't do that here. So pretend that on the left here you have this continent, which would be India, and over here is Asia, and subduction has started. And watch what happens here in the middle as this moves to the right. It's starting to crush and fold, even causing some faulting here. Do you see that? There's some, if you look in here carefully where the collision's happening, you'll notice that the rocks fold and then they reach a point where they can't fold anymore and they actually slip or fault. It's in this orange area right in here, or this yellowish area where you'll notice it the most. If they zoom in here in a moment, you'll see where it's sort of an offset. See how there's some give, or it broke, especially on the left side. All right, so that's very similar to the faulting and folding in Virginia's Valley and Ridge. Okay, and isn't that impressive? You can really tell that this model is mimicking rock layers being deformed in continent to continent collisions and producing the mountains. Okay, and we even get these trapped rocks in between in mountain ranges where you see sedimentary rocks that are pinched in between continents. We can actually find those in the actual mountains. Here you can see this V-shaped valley here on the left side here, and now it's in the middle. That folding, the only thing this model doesn't do is show erosion. These mountains have been eroded, so you see some cut off folds because erosion is cutting, glaciers are cutting those mountains. Okay, that's it.